Okay, well, welcome back to another one of our little podcasts. And today, Phil over in London town over there, and me over in Gloucestershire City. Well, it's not actually, it's in the countryside. We're going to be talking about audio. A bit of a basic audio 101, audio fundamentals, the ins and outs and what have yous. And Phil, I know you've been doing a lot of work which involves audio, and I know you've got lots to say on it. But before we go very far, I want you to tell us, what is sound?
Well, before we go any further, I'll just point out this nice new Heil PR35 microphone, which I've got here. Not that I've purchased it or anything; it's for a job that I'm doing next week for a commentary position for a football club. So I thought I'd break it out of the packaging and use the customer's facilities for one go.
Well, yes, all in the name of testing, and I'm sure we can use it as a jumping off point for some questions later on. In fact, as we're going, because when you're telling us about what sound actually is, it might help to explain why you've got that microphone close to you and what goes on inside it. So build it into the story.
Well, I mean, sound. It's that sensation of vibrations of air hitting our eardrums. So I've got a couple of earbuds, stuffed in my ears so I can hear Hugh over the Skype. And they're delivering vibrations in the air within my ear canal straight to my eardrums. But, the principle of you kind of walking around, the town where you live or whatever, and hearing vibrations in the air hitting your eardrums, that's what we call sound. That's the nature of it. It's a very physical thing. It's a very analog thing. And it's the result of physical actions. Trees falling over, guitar strings being strummed, cars driving past you. They cause vibrations in the air, and those compressions and rarefactions, so those squashing up of the air molecules and pulling apart of the air molecules, as they hit your eardrum, they cause your eardrum to vibrate in a similar fashion. And by the amazing nature of the way your ears work, your brain gets that signal, and you can interpret what's the sound that's coming into your ears and what's going on around you. So
you need the air to transmit sound. So it's true what they say, in space no one can hear you scream. Why is that?
Indeed. Well, there's no medium for the sound to be transmitted through. There's no air molecules for the sound to bash into each other, to make it into your eardrum, to vibrate your eardrum, for your brain to say, "Hello, what's that noise? It's a lion roaring. I better run," or whatever.
Inside your ear, there's actually connected to the eardrum. There's after a sort of mechanical connection, there's little hairs, aren't there, which wibble bits of brain, as it were, little cells.
That's exactly right. There's the cochlea, which I should have prepared this ahead of time, but let's see if we can pop up a nice image of it off the Googles. There's got to be something here that looks suitably explanatory. Let's have a look at that.
Sorry, viewers, I have thrown the great man already.
So this is a little picture here showing how Cochlear Implant works, which is a gadget for people who've lost some of their hearing, and it's a microphone and an amplifier externally fitted to the outside of your head, and then inside there's a little implant that goes straight into the part of your ear, that cochlea, that coiled up tube, which in a healthy, functioning hearing person contains, like you've mentioned, Hugh, sets of hairs of varying lengths and rigidities, which allow you to perceive different frequencies of sound. But in the case of somebody who's suffered hearing loss, an electrical cable is placed in there to provide a similar nervous stimulation to replace that lost auditory ability. So again, you've got that vibration of air being translated into vibration of the eardrum, being translated into vibration of the fluid within your cochlea, within your aural canal, vibrating those tiny little nerve hairs, which then your brain is then able to interpret as varying frequencies, varying sound loudnesses, giving you access to the rich worlds of sound around you.
Yeah, absolutely. And I think it's worth pointing out that although we are both sort of techies, and all our viewers are techies, we have digits, we're all analog beings.
That's exactly right. It's that whole kind of thing of digital good, analog bad. But the truth of the matter is, we live in an analog world, and that's exactly what we're after. We're after a faithful reproduction of that analog waveform, a faithful capturing and transmission and such like of the analog waveform. And I'm just popping up a screen capture from a digital audio workstation. I think it's Adobe Audition that I use at home, which shows the simplest kind of sound you could have. It's a sine wave, and if you are a television or film person, you know what a test tone sounds like. It's that constant, and in fact, I've got Audacity running here. I should have, if I have a look at my Audacity, I've got a tone here, which if I play, so there's Hugh whistling away at exactly 1 kilohertz, and that's a commonly used signal within our industry for calibrating, for testing that signal paths work, and it's the simplest sound that can be produced because it's just a sine wave. As you get into more complex sounds, you discover that actually even the most complex waveforms, human speech, music, things like that, can, when a special kind of mathematical transform is applied to them called the fast Fourier transform, they can be broken down into a finite number of sine waves. Right. So that in fact, I've just zoomed in on the 1 kilohertz tone we were listening to, and you can see, the seconds across the top, which I think previously I had 10 seconds of the tone running across the top. Now I've got, I'm at 3.88 seconds, 3.885 seconds, 3.890 seconds, and you can see, there's what, 10 or so cycles of that tone between, 2/200ths of a second. So there's a lot going on time-wise. Audio is a rich business, and I suppose that means we should really talk about those two different aspects of audio: the frequency of a sound and the intensity of a sound, because they're entirely separate from each other. They're entirely different items. The frequency of the sound is what we perceive as pitch. It's what musicians refer to as a note. And, if you have a very simple sound like that tone, which I'm playing again, that's just a single frequency. And as we all know in television, that's 1 kilohertz. That's 1,000 cycles per second. And that's all it is. Now, the tone I happen to have up at the moment is of a sort of average program level. It's marked as neg18 dBFS. That's the name of the file. But we'll get onto that a bit later, because
yes, please,
that's not a particularly intuitive thing. I'll pop up another example of test tone, and although this is entirely the same kind of sound, so I'll play it. Sounds exactly the same, but this is neg18 dBFS, so that's a different level again. And in fact, if I pop back to the window with the neg12, you can see that that's a considerably bigger waveform than the neg18. So although they sound the same, they have the same musical note, if you will. That they've got different levels. And what do the different levels mean? Well, the different levels mean that one's louder than the other. In the case of the air travelling to your eardrum, for you to be able to perceive it, that's the difference between a very tiny amount of vibration of air molecules and a very gross amount of vibration. And in the case of sound going down the cable from this microphone into my little mixing desk, into this computer that's recording our session, that's a greater variation in the voltage level going down the analog cable, or it's a greater variation in the digital levels as they're recorded onto the hard disk of the computer. But the frequency is an entirely independent item to the level of the sound. It's the intensity, the loudness of the sound. And so let me find another example of a waveform. So this waveform is labelled sweep. So that might give you a clue as to what's going on here. So if I start playing the waveform from the start. And you can hear from the get-go that started off at a very low frequency. If I go all the way back to the start again. And very quickly kind of goes up through the kind of frequencies that were, you'd expect, musical notes, those kind of things. And by now it's kind of up there, very sort of nasty frequencies where dogs start barking. And in fact, it was still playing after I stopped being able to hear it.
Yes.
So that kind of tells us that there are notes that are very low that you can only just about hear, and there are notes that are very high that you can't hear. And in fact, as you get into your middle age, you start losing those high notes.
It's all too true, actually. Yes, you really do. You notice it.
And I mean so when you're a fit young fella, a young teenager, you can hear typically from about 20 hertz, 20 cycles per second. That's a very low note, all the way up to about 20 kilohertz, 20,000 cycles per second, very high note. By the time you're in your 40s, like me, you're kind of down there in the low teens. So I can remember when I first joined the BBC, when I was in my early 20s, I could hear all the way up to about 17 kilohertz. Now I can hear up to about 14 kilohertz, maybe 13, 14 kilohertz. And so it's clear that as I age, those tiny little hairs in my ear are starting to die off. The little short ones that detect high frequencies are starting to die off. And so my hearing is starting to roll off, and I can hear fewer and fewer high frequencies. And the sad irony is that kind of by the time you're making good money and you can afford decent hi-fi, there's no point because you can't appreciate it.
It has another mix. So I know we're straying off the point. We'll come back to it in a minute, but it does have a bearing on if you're doing recordings for people and you're doing any sound balancing, because of course you're going to overcompensate if you're not careful. Also, and it just reminded me of a story. I was doing some recording for a band 2 or 3 years ago, and the guitarist, as opposed to the rest of the band, the guitarist was really quite hard of hearing, particularly in the upper ranges. And he said, well, no, it sounds really muddy. By the time I'd EQ'd it for him to like it, it sounded dreadful, even to me, and especially to the rest of the band who could hear rather well. So, yeah, you have to be quite careful. He was unaware that he had this hearing loss. So.
And did you have enough EQ, enough parametrics on your desk to be able to give him a separate EQ'd monitor feed?
Not really, no.
Okay.
Quite a small mix, but yes. It made the production of the final recording rather awkward on account of he said, well, it doesn't sound very good. But you have to listen to it compared with everything else.
Yes,
anyway.
Yeah. So
I don't.
No, not at all. So we've seen what we call the sweep, which is a recording that starts at a very low frequency and works its way up to a very high frequency, but by looking at the waveform on screen, there's no variation in level at all. That level doesn't change. I'm sorry about that, Hugh. So let me pull up another waveform here. I've got this waveform is called ramp, and if you're looking at my screen capture here, you'll see that it starts off quite a low level and it increases in level as it goes up. But clearly, that hasn't changed frequency at all. So it's just really to emphasise that point that sound is frequency and it's level, and they don't really relate to each other. They're entirely separate entities. But so far, we've only really listened to test tones. We've listened to those very simple sounds that are just composed of a single sine wave. And in the case of the sweep tone, the frequency of that sine wave varied across the 10 seconds that we played it. Varied from about 20 hertz, that very, very low note, all the way up to 20 kilohertz, and I kind of stopped being able to hear it after 7 or 8 seconds because it had gone off the end of my hearing. And in the case of the ramp, we went from between about neg 18 dBFS, which I'll get onto these levels a bit later, up to about neg 12 dBFS. So we went up 6 dBs. We doubled the intensity of the sound, but it was obvious that it hadn't changed the tonal quality, the musical note. So if we put that all together, and bearing in mind that we only ever hear test tones, we only ever hear single tone notes at the start of videotape, or when things are being calibrated, you never hear those in reality. So I've popped up now a waveform of a man's voice. So you can see it's a considerably more complicated waveform than those test tones that we saw. I'll just play that.
Starts with.
So it's a man saying it starts with. And you can see there's a huge variation in frequencies. There's a huge variation in levels, and that's what gives sound its richness and its variability. The fact that you've got these two variable things, frequency and level, and they can vary very, very quickly. And all of a sudden, you've got not just musical notes, but you've got people's voices and all the richness of
all the sound.
The worlds around us. So let's pop up a little bit of an audio recording of of some music, and I'll just zoom in on the first bit. We'll play that, and you can see that opening piece, and it's very obvious from looking at the waveform what we're seeing. You can hear the that plucked guitar at the start, and it's just on the right hand channel. And then I suspect the vocal comes in now.
I can ride my bike
So you can hear there's a bass guitar, there's an affected vocal and all that kind of stuff, and I'm sure I nicked this off my kids. But you know, music again is an awful lot more complicated than if you look at it, it's more complicated than the recordings of voices, because not only are there voices going on, but there's different instruments in the mix, and you know, I'm just zooming in on this one, and you can see the huge, just over a bar of the music, huge variation of frequency and level. So you just remembering that sound is a very complicated business. And
Indeed it is.
All that richness is due to harmonics. So what are harmonics? Well, those very simple sounds we heard at the start, the test tones, that's just a single frequency, and there's nothing there to write home about. And in fact, that tone I was playing you was 1 kilohertz, which, if you're musical, is not quite 2 octaves above middle C. Middle C is 262 hertz, and an octave in musical terms is going from a C to a C or a D to a D on the keyboard or on the guitar or whatever. But in engineering terms, it's a doubling of the frequency. So a middle C is 262 hertz, so an octave above middle C, so musically the same note, sounds the same, you know, you could play it on the keyboard an octave up and it would sound good, is 524 hertz. And I know that two octaves above middle C is 1048 hertz, which has been a sort of a naughty little sort of self-indulgence of mine, that whenever I'm setting up signal generators in facilities, whenever I've built a facility and I've got to set up the SPG for the audio test tones, I always set them to 1048 hertz, because that's a musical note rather than 1000 hertz, which is a tiny bit of it's a flat flat C 2 octaves up. However, this has started to bite me in the backside, because recently the company I work for, we've started selling file-based QC software, which one of the things it does is it will look for audio test tones either at the head of a tape or if they appear in the middle of a program, which you never want, and it will detect it. And 1048 hertz it doesn't get every time, because it's sufficiently far away from 1 kilohertz, which is what the EBU says test tone should be, that it's a problem. And I'm just sort of, you know, fearing that tapes made in facilities that I built are going to get run through this software and it's not going to detect problems, because I thought that 1048 hertz, 2 octaves above middle C, sounded nicer rather than 1000 hertz. So just a little thing to worry about.
There you are, there you are, everybody. We heard it here first. The end of an excellent career.
So getting back to what that mentioned about harmonics. So that 1 kilohertz tone has no harmonic content at all. It's just one frequency. But if you look at the let me spin this recording of the popular tune back again, and let's bring up one of those plucked guitar notes in greater detail. So there that is. Let's just zoom in on that. There we go. Plucked guitar note, and that doesn't just contain a single frequency, although it is a one musical note. Because it's a musical note that's come off an acoustic instrument, it has there'll be the fundamental note, which if that was a middle C, it would be 262 hertz. But as well, there's also some third order harmonics. So there's I'm just noticing our podcast visitor.
I'm so sorry, everybody.
Fantastic.
This is my little boy who's just come in. So yes, I don't know what you're doing. But anyway, sorry, you lost your flow.
Get them young. That's what I say. So as well as a fundamental frequency in the audio in the musical note, there will also be a third order harmonic, which is that frequency times 3. There'll be some fifth order harmonics and odd order harmonics going all the way up to quite high up, and it's those harmonics that give the sound its richness, and it's what you get from instruments built of wood with nylon or metal strings strung on them. You get very rich harmonic content. If you look at the waveform of a violin, which has lots of harmonic content, it doesn't look anything like a sine wave. You can see that there's a fundamental frequency with a repeating pattern to it, but there's an awful lot of other things going on there as well. And so harmonics are what give musical notes their richness. and recording engineers will go to great lengths to avoid harmonic distortion, to avoid filtering effects where they lose some of those rich harmonics. And it's why digital compression is a challenge, because it means not only have you got to compress the fundamental notes of the music, you've also got to be able to faithfully reproduce the harmonic content of those notes as well, for it to sound nice, for it to sound good to your ear, for it to sound like the guitar you've heard before.
So a harmonic is actually not a terribly complicated thing. It's just more sine waves. If we said our fast Fourier transform, which I can't remember how to do, but I do remember bleeding in the brain trying to do them a long time ago, having to do these things by hand. But you start with a sine wave, say a nice simple 1 kilohertz tone, not terribly interesting. Try and reproduce that tone on a real instrument, say a violin. You will get that 1 kilohertz tone. You'll get a whole load of others too, which are multiples, submultiples of that tone, and other sounds, of course, which might come into it. And am I right in thinking that that's what we're talking about here?
Yeah. So as broadcast engineers, our intention is to be able to faithfully capture and reproduce, complicated sounds. And the harmonic consideration is it's right up there. It's why telephone lines sound the way they do, because they're kind of rolling off at about 8 kilohertz. You think, well, hang on, there's not much. Sorry, 4 kilohertz. You think, hang on, there's not much content in the voice really above 1.5K. Why do telephone lines sound so rubbish? And it's because
in fact there are lots of harmonics.
All the harmonic content's gone, and it just doesn't sound like it sounds when I'm talking to you face to face.
Yeah. Yes. So yes, absolutely. The early voice synthesizers, which used very nearly pure tones. What was the name of that recording from years ago? Chalky? No, not Chalky. Sparky, the talking piano.
Yes, yeah.
No harmonics. Very simple tones. Horrible.
Yeah. Now, so part of faithfully reproducing that sort of sound chain, from microphone all the way through to, earphones or speaker on a television or whatever, is thinking about how the sound is represented. So obviously, it comes out of my mouth as a varying pressure in the air. It's captured into the microphone, and the diaphragm in the microphone, depending, there's several different technologies. This is a moving coil microphone. That generates tiny magnetic variations that travel down the cable into the audio mixer. The audio mixer gets those up to sort of slightly higher levels and allows you to mix in other, line level things, the level that's coming down from Skype, etc. And then that's a slightly higher level of audio signal that's being captured into this computer, and the computer's storing it on hard disk. And then at some point, it'll no doubt be compressed into something like MP3 or AAC or something like that for delivery as the podcast. But all through that process, it's can we faithfully reproduce the frequencies, the levels, all the rich harmonic content that makes up the sounds we want to listen to. In the case of vinyl records, many years ago, the variations in loudness were stored in the depth of the groove. If you need to digitize and manipulate sounds, they're stored as numbers on a workstation or on a CD or something like that. And as we think about digital representations of sound, the thing that you might hear come up often is this idea of the Nyquist limit. You often hear people talk about Nyquist. What's Nyquist? Well, Nyquist was a German physicist who figured out that to accurately represent, it's not just sound, but any signal in the digital domain, you have to sample it at a bit more than twice the highest frequency you encounter. I think actually it's the mathematical constant is 2√2. So it's about 2.8 times what it should, what the frequency is. So in the case of CD, because we need to be able to hear up to about 20 kilohertz, a CD samples at 44,000 samples per second. And in fact, that's probably the lowest of the digital systems we deal with nowadays, because most digital professional audio is 48 kilohertz sampling, or in fact, increasingly for film and things like that, 96 kilohertz is preferred.
Yeah.
So you can see that analog waveform coming down the cable into my mixing desk, into my computer, that has to be chopped up into many digital samples, and those samples, in a sense, the signal is safe at that point because it's been captured, and that it's not then bedeviled by distortion on the line or by noise or those kind of things. But still, you've got to bear in mind that at the end of the process, it's going to come out of a loudspeaker and be turned back to an analog signal to get into your lug hole, so you can hear what the program producer wanted you to hear.
Yep, that makes sense.
Now, as well as having spoken about frequencies, and we made a great point about frequency and levels not being the same thing, being entirely unrelated to each other, when considering a digital system, you have to think about the dynamic range. What's the difference between the quietest signal a system can encompass and the very loudest signal it can encompass? And the human ear has a fantastically wide dynamic range. The difference between the very quietest thing you can hear, a person whispering in the room next door, and the very loudest sound you can bear, at a very loud gig or whatever, or standing near a jet plane when it's taking off, that is a huge dynamic range, something in the order of 140 dBs. And we'll get back to dBs again a bit later. But the dynamic range also has to be considered when making a digital representation of the sound. And the dynamic range in digital terms is how many bits you use to encompass that waveform. So I've got a sine wave up at the moment, and you can see, if we zoom right in on it, you can see it's steppy.
Yes.
And it's just kind of steppy enough for it to be recoverable at the other end. And so in professional applications, 16 bits, or that equates to 65,000 levels, is common. That's CD. Or increasingly 20 bits is what we'd use in professional applications. And in fact, 24 bits is becoming very popular in film. That's for recording huge, great orchestral pieces, for mixing. 24 bits is very common. So that's how a digital recording captures the variation in level, and by the number of times you sample per second, how it captures the frequency of the signal you're trying to deal with. And in the case of analog audio, which is for people to listen to, we need to go from very low, 20 hertz, all the way up to 20-something kilohertz for the youngsters. And, in level terms, we have to go from, very, very tiny signals all the way up to very, very loud signals, which typically needs at least 16 bits to faithfully reproduce at the end of the day.
Okay, this we've been talking about these levels. Is this a good time to try and standardise what we mean by levels and introduce, I don't know, some way of comparing one level against another? Well,
back in the old days, when everything was a recording on magnetic tape, and every signal travelled down an analog cable, we really only had to know about two things. You had to know about the intensity of the magnetic field on the tape, i.e. how a level on the cable equated to a magnetic variation on the tape. That's really all you had to know about. And so we'd commonly say that we were sending 0 dBUs, which is our kind of preferred lineup level in analog terms in broadcast. We're sending 0 dBUs down a cable, and 0 dBUs, that's not a very sort of intuitive sort of thing to say. That equates to something around about 0.773 of a volt, full scale, into a 600 ohm load. That's not something you need to remember. That's a very analog and historical thing. But that's where 0 dB...
It was a certain amount of energy being disposed of, wasn't it?
Exactly. How much a 600 ohm resistor heated up if that signal was being applied to it. So that's where it all dates back to.
So that was an attempt in engineering terms to try and set some sort of known level, some measurement where we could then start taking measurements from.
Yes, the zero level. And that was often called 0 dBu. And the U refers to that 0.773 of a volt into a 600 ohm load. You quite often hear people talk about audio levels and they'll just say, it's 15 dBs, which is meaningless because a dB is merely a difference. It's the same kind of thing as a percentage or a fraction. It doesn't say anything itself. You have to qualify it with a dBUs or dBAs or dBFS in the case of digital signals. It's quite legitimate to say, that signal is 6 dBs louder than that signal, or that signal is 10 dBs quieter than that signal. But you can never say, this band was so loud, we were getting 120 dBs of sound. That's meaningless. And you hear
compared with what?
Yeah,
and
exactly.
How are you measuring it? Yeah.
And kind of what comes to mind is my old physics teacher saying, "Units, boy. What do you mean dB?
Yes.
dB elephants? What do you mean? So you have to specify what kind of dBs you're talking about, because a dB itself is just proportion. It's just a ratio. It's just a percentage equivalent. So in the old days, we had an analog level going down a cable, and we talk about it in terms of dBUs. 0 dBu being the line-up level, 0.773 of a volt into a 600 ohm load. Nowadays, we talk about digital levels, going down a digital cable or being recorded onto an Avid's hard disk, a digital level on the hard disk or whatever. And we talk about dBFS. The FS stands for full scale. And so we're talking about decibels below digital full scale. So whereas in the old analog days, and I've got a little picture up of a ppm, a VU, and a digital meter. So whereas in the old analog days, the needle's pointing straight up at the 4, that was considered 0 level, line-up level, very good. In the case of our digital meter, in Europe, our standard is neg 18, so 18 decibels below digital full scale is where we like our line-up level to be. That's the equivalent of our old 0 dBu analog line-up level. And on a properly calibrated piece of equipment like an Avid or a digital VTR, if you apply on the analog inputs to the VTR a 0 dBu signal, the digital level recorded on tape or digitized onto the hard disk would be neg 18 dBFS, and that's on a properly calibrated machine. And similarly, if you popped open your Avid calibration tool and played out neg 18 dBFS tone on a properly calibrated output stage, 4 ppm, that's the equivalent. But there's no fundamental reason why neg 18 was chosen to match 0 dBUs, only that it was.
And indeed, if I recall correctly, taking delivery of digibetas and things from Sony, which hadn't been adjusted correctly. Was it neg 20 they were coming in from?
Neg 20 is the American standard. So the Americans to this day still assume neg 20 is line-up level. And so there's a 2 dBs difference, which isn't enough to be able to hear it on program, but it's enough for the guy in the QC suite to throw the tape back at you and say, the audio's 2 dBs wrong. And so my little picture I've got up at the moment shows the ppm, the VU, and a digital meter, and gives the the delta between the graduations. So on a ppm meter, which is an old BBC standard that goes back to the war, that each of the big graduations between 3 and 4, 4 and 5, 5 and 6 is 4 dBs of difference. And
now, just let me stop you there. When we were talking about the dBs, you mentioned how many dBs was a doubling.
Yes.
So just refresh us on that.
So the decibels is when applied to sound is a logarithmic relationship. The difference varies depending on how many dBs there are. But a very quick and nice thing to remember for engineers is that 6 dBs is a doubling of the signal level or a halving of the signal level. So you'd say, can you wind that up by 6 dBs? What they really mean is, can you make it twice as loud? And 20 dBs is 10 times, give or take. It's almost exactly 10 times. So if somebody says, I need a line level amplifier that gives me 20 dBs of gain, you know that it's going to boost the signal tenfold.
Right.
And they're just 2 handy things to remember. It kind of might get you out of trouble. So the ppm.
Yeah, back to the ppm.
Yes, so ppm, 0 level is represented by 4 on the ppm, and on a well-mixed program, the peaks aren't meant to really much go above 6 on a ppm. So only 8 dBs of difference between the lineup level and the peak program level. And the program kind of would average around about 5 on the ppm. A well-mixed, well-finished program that had been through the audio suite, you'd expect that to be the case, that program averages about 5 on the ppm and rarely goes above 6 on the ppm. And in fact, a modern ppm, I've got one here, pulled it out of the demo stock just to show you. A modern ppm, as well as having the meter movements, which we've got up on screen at the moment, also has some LEDs. So next to each of the meters, you can see that there's an LED marked peak, PK, and that blinks on when your needle goes just past the 6 on the ppm to warn you that you've gone past peak. And once you're kind of into 6.5 territory, it's on pretty constantly. So once you're kind of 10 dBs hotter than lineup level, it's on all the time, and you don't want that because depending on how fussy the broadcaster is, they might throw the tape back at you or the finished program back at you if you're getting any peaks. The BBC tend to be more tolerant, and they tend to only throw things back when there's gross peaking.
And there's a good reason for that, because further down the transmission chain, if you start, especially not so much these days, but in the old days, if you overcooked it, you would start producing harmonics at the transmission, and those harmonics would be different frequencies into other people's receivers. So it had a real meaning. I mean, nowadays they can trap it. In those days, you needed to get it right for it to work properly at all.
Yes, well, obviously this all dates back to analog levels, doesn't it? It's an analog transmission, and so if you imagine you're a radio station with an FM transmitter, or UHF television station, where the signal level is directly modulating the klystron that's sending a big RF signal, 600 whatever megahertz out of Crystal Palace, you really have got to make sure that things are correct, because if they aren't, one television channel might bleed onto the next one, and you get modulation. And old people who remember old-fashioned sort of analog-only television sets that maybe were valve-based, they'll remember when you had particularly loud sounds that was sometimes modulated onto the pictures, and so there were sort of unwanted analog effects which occurred if you didn't pay attention to those levels.
And may just be hearable still on some of the pirate stations, especially in London, where there's lots, some over-modding going on there. Anyway, we're moving off a little bit.
No.
There we are.
Pirate radio is fantastic, and if you listen to the Adam and Joe show on Six Music, and you can find it on the Six Music website, they've got a fantastic show about pirate breakthrough, which if you live in London and you drive around, you often get, you're often listening to Radio 2 or Radio 4 or whatever, and all of a sudden you get the yes, very, very sort of over-modulated pirate radio sort of coming through. So I encourage you to go and listen to that, because that's very funny, Adam and Joe's take on pirate radio. But that aside, and of course pirate radio people don't use proper measuring devices, because they, But
it's hardly pirate, is it?
No, that wouldn't be cool for school. So I've just squizzed along to a VU meter. A VU meter is fundamentally similar kind of gadget to a PPM, except it's an American device. It's what the Americans use as opposed to what we use in this country or Europe. Very similar, except the lineup level on a VU meter is at neg4, which is the needle pointing straight up. Each division, each big division is 4 dBs, as the same. Each little division is 1 dB, and so the average program level would be 0 on the VU meter, and peak program level would be at the end stop, i.e. 4 dBs above that. So there's some argument that VU meters are directly driven by the signal level. So a VU meter will flip up and down very quickly, whereas a PPM has a more graceful, sort of weighted response. So with a PPM, it will rise.
Sluggish would be a term you could use, I suppose.
Yeah, and it's the intention is meant to give you more of a representation of how the ear works. It's more representation of how it sounds to you, rather than what's coming down the wire at that precise instant.
But, and I know you're going to be talking about it a bit later on, when we're talking about transients, very short pieces of sound, which can get through a chain of digital equipment much better than it could in the old days, you can run into trouble because you've run out of headroom, which I know we'll get to. So sometimes a PPM won't tell you the whole story, hence the little red light, I suppose.
Yeah, and it's pertinent to say, because back in analog days, analog recording degrades gracefully when you hit the end stop. If you're over modulating a piece of magnetic tape, so you're making a recording onto a Studer, an A80 or whatever, and you've made your lineup recording, so you know that it's been modulated at 160 nanovebers per meter squared, but please don't remember that. But that just happens to be the signal level on tape for 0 level.
These guys did.
Look at that! That's a Nagra.
Yes, it's a Nagra SN. I don't know if you'll be able to read it off this thing, but it's actually got a completely different scale. I was thinking it was a VU, but the scale is actually more like a digital meter in that it's labelled 0, a quarter, half, 3/4, and full or 0. Can't quite see it there.
Is that what the Germans used to refer to as a DIN meter, a DIN audio meter?
Oh, it might be, yeah. I don't know if I really don't think it's going to pick it up for us, but you might just, if it'll focus.
That's great.
No, never mind.
That's brilliant.
But yes, known magnetism.
Yeah, so you overmodulate a piece of magnetic tape and it degrades gracefully. Initially it just doesn't take the flux as well as it did, a few milliseconds ago, but it doesn't sound nasty, and that's why recording engineers kind of quite like tape, because it has a nice way it degrades when you overmodulate it. But in the case of digital recordings, as soon as you hit the digital end stop, it sounds awful. You've run out of dynamic range, and it's just that the waveform is clipped, and that in itself brings in a load of low order harmonics, and so you can't overmodulate a digital recording without it just sounding appalling, and that's why our digital lineup level is neg 18. And you think, well, 18 dBs of headroom above the lineup, that's an awful lot, isn't it? But you really need it with a digital system, because those transients, those momentary spikes in the signal, which wouldn't particularly be degraded too badly by an analog recording medium, because they're only momentary, and the magnetic flux is kind of good. On a digital system, it sounds awful. You get a splat. It sounds terrible, and that's why we seemingly need a lot of headroom in digital signals. Because so if you think about, let's go back to our PPMs. You think about our peak program level on a PPM. It's six on a PPM, which is 8 dBs above zero level. So it's plus 8 dBUs on a digital scale. That's 8 dBs above neg 18, so that's neg 10. You still got 10 dBs of headroom between the peak program level and digital max. But we need it because transients are nasty little things which just sound awful in digital systems.
And in an analog recording, especially on a magnetic recording, the tape would have saturated at that point. It wouldn't have sounded awful. You just wouldn't have heard it. We would have rolled off quite comfortably. But in a digital world, yes, it'll respond. It runs out of digital word. It just produces a horrible splat or a click or whatever nasty effect. So you need to be able to avoid that. So, but of course, the upside is that if you record much lower down, you can still record faithfully in a digital world. Whereas in the analog world, you had to cope with the noise of the vinyl, the noise of the of the raw magnetism. So you were above a sort of hiss, which old boys like us will remember. The youth of today are spoilt. They have no hiss in their lives.
No, that's right. On the odd occasion that I play my kids old recordings that were made on analog tape, the thing they always say is, turn the gas tap off.
Well, yeah.
So I've just popped up we've obviously we just looked at those three styles of meters that you see on the front of VTRs or the front of other audio equipment. I've also just popped up a screen grab from a Tektronix WVR series rasterizer in its audio mode. And it's showing a
yes, very nice.
So it's showing a 5-1 recording, so a 6-channel, left, centre, right, left surround, right surround, and the low frequency effects channel, and then a derived stereo mix from that. And it's got the Lissajou display up to show phase. And when these things are running, they're quite sort of entrancing to look at, hypnotic almost. You could kind of they're very nice. And so you can see that in our multi-channel world now, we've gone beyond stereo. We need sort of slightly more sophisticated audio test sets than PPMs and VUs, and even digital meters. We need slightly more sophisticated test sets to be able to monitor our surround sound recordings. But we're 44 minutes in, Hugh, and I kind of think maybe that's a good point to end this 101 recording. I think next time I'd quite like to talk about the more sort of engineering-y things, how we connect all this stuff up, Crone frames.
I think that's a good break point. Yeah,
digital
absolutely.
audio. So we'll probably say goodbye and come back with the more engineering side of audio. Is that fair enough?
I think that's a great place. So very quickly recap. We discovered that sound is air pressure or requires some sort of medium. Air is what we tend to live in.
Water as well. You can hear stuff underwater.
Water will work as well. Absolutely. All material moving will work. But because we're largely, when we're talking about sound, we'll be talking about sound in air. And that has all sorts of ramifications, but we won't go into those. We know that we're interested in the intensity of sound, i.e. how greater pressure there is, and we're interested in the frequency, how that pressure changes. And then we looked at ways of creating some method of discussing it, some base level of measuring it, and we introduced a logarithmic scale, the decibels, and we talked about the the relationship between a sound at one level, a sound at another. And we also talked about producing that as an analog electronic signal and a digital signal, without going into how we do that. But we talked about it, and some of the things that run away from that, making sure you get the levels right and why you'd need to bother. And then finally looking at how you'd represent those in mechanical meters or digital what have yous, bar charts. So I think we've got all that. The next time I think we will want to talk about how you'd physically get a sound from this place to that place, and whether or not you use a pair of handy croc clips or something more sophisticated like connectors. So there.